On the 25th of March 2026, Discord had an outage where its voice service was down for 2 hours. And in 2021, something similar happened in Slack where millions of users couldn't connect on a Monday morning. These are not beginner teams. They are well-resourced engineering teams that will not make beginner mistakes. And they've spent years fine-tuning and managing this product. Both outages trace back to the same layer, which is the WebSocket-backed infrastructure for their products. And this video is mainly about communicating what it entails to build and manage a system like this. There are several things we want to consider before embarking on a project like this, which is a real-time infrastructure project. And we are going to be discussing 5 of them. The first thing we need to discuss is the common belief about WebSocket, which is not actually completely wrong, but let's just discuss it anyway. So most engineers, when we think about scaling WebSockets, we just think about adding a new server. And this is enshrined in the fact that we believe that WebSocket is just a stateful HTTP, which is not completely wrong. Actually, it's correct, but this assumption would cause some issue down the line. This takes us to number 2. Why this belief exists. It exists because of the education gap. Most tutorials you see and videos and articles talking about this would only talk about a single server communicating with several clients or a few clients, and that's generally the setup. So let's take a look at this. So this is usually what is shown in tutorials to show how WebSockets work. You have a single WebSocket server, you have several users connecting to this single WebSocket. What they don't show you is when you have 10,000 users simultaneously sending messages on a single channel. And this is what most engineers assume scaling will entail. So you just add a new server and add a load balancer in between, or a cluster of load balancers in between. Your users communicate with them and you spread the load. But things are not this simple. So we are going to talk about the failure mode very soon, but let's still talk about the third thing. Let's talk about issue 3. Up until this point, I assumed everyone watching this video understood what a WebSocket is or WebSocket protocol is. But just so that everybody can be on the same page, I'll just do a very simple explanation. So let's go back to this diagram. The simplest way to understand the WebSocket protocol is just a TCP connection, just a connection between user 1 and the WebSocket. And it is in such a way that the client can send message to the server and the server can send a message to the client. So in this diagram, for instance, user 1 can send message to the WebSocket server and WebSocket server can send a message to user 1. So if user 2 sends a message to this WebSocket server that also has the states for the connection to user 1, then the WebSocket server can forward the message from user 2 to user 1. Which brings us to issue number 4, which is when you introduce a new server, things start getting complicated. So let's just follow this simple illustration. If user 1 connects through the load balancer can decide to send the user 1 to the WebSocket server 1. And as we discussed, the connection state is going to stay on server 1. So when user 2 comes, the load balancer can also forward the message, forward the connection to server 1 also. So we have these 2 users connected to WebSocket server 1. Let's say we have user 3 and user 4 connecting through the load balancer, and the load balancer decides that he wants to send them to this server 2. What now happens is that when you have messages from user 1 and you want user 4 to get the message, it should be impossible to get them because the WebSocket server 1 does not have the knowledge of the connections on WebSocket server 2. So the only way you can pass the message along would be if these 2 servers can communicate with each other, which is what we are going to be discussing in this server. And we've actually already spoken about a failure mode, but we will still talk about it in depth. And then also you don't have to persist the connection through the load balancer. You can just have something like a broker service here or a routing service here that is going to find out which servers are available. So this service can be aware of the number of WebSocket servers that are connected to it or that are live, basically. So when user 1 comes along, it tells it to connect to WebSocket server 1. And when user 2 comes along, it tells it to connect to WebSocket server 2. So this is another way you can go about it. Although it might make management a little harder, but it's still a method that you can go through it. And this actually shows very well how these 2 servers are not related. Yes, this second server cannot possibly know about messages sent by user 1 because it doesn't have the state of that particular connection. So this will take us to the last issue, which is issue number 5. What does a real WebSocket infrastructure look like? What I'm going to be giving you is an extremely simplified version, but it would show you what it should entail. Yeah, so we have basically what we had before. we have several users connecting through a load balancer. This could be a cluster of load balancers, and you can make it as complicated as you want it to be. Then connecting to a cluster of WebSocket servers. So now, because the WebSocket servers would typically have to do a lot of things like authentication and getting some user data, if they need to get that, they would need to communicate with another backend service or a backend server, and they could do it in process, but typically you would want to do it on a separate server. Then they would have a message broker that would communicate between the two of them. Okay, so this is the simplest way you can have a WebSockets infrastructure. You have users, a load balancer, a cluster of servers which communicate with a message broker. Okay, so let's just illustrate how messages will go through this system. If the four of them are connected to these two servers, so we'll assume user 1 and user 2 are connected to WebSocket server 1, and user 3 and 4 are connected to this other server. These two servers will connect to a message broker that typically can handle a lot of requests. So they should have a way to scale vertically. Kafka scales vertically, and you can also have Redis cluster. So if user 1 sends a message to the server 1, the server 1 sends it to everyone that is connected to this server, which is user 2, and if you want, back to user 1, then also send it to the message broker. And since the WebSocket server 2 is connected to the message broker, then it can also receive the message sent by server 1. And when it receives it, it has the state or the connection to the other users, and it would send it basically to this two. Then this way you can have multiple servers handling the load for a lot of users, and you basically scale. At scale, there are several ways your WebSockets can fail. And the first one we'll be talking about is the reconnection storm. So let's still use this diagram as an example. So let's say each of these users, they represent, let's say 10,000 users. And so this will be 20,000 users. This will also be 20,000 users. So this server is handling 20,000 users. This also is handling 10,000 users. The reconnection storm happens usually when a lot of users are trying to connect at the same time. And if you have a lot of users trying to connect at the same time, then you can overwhelm the servers that are available, or even your load balancer if it's not in a cluster. So for instance, let's say server 1 dies. So if server 1 dies, we would sever this connection, and these two, we are going to delete these connections. And then these two users will try to reconnect. Actually, these 20,000 users will try to reconnect at the same time. So this load will be happening simultaneously on the load balancer and on this WebSocket server. And now when a reconnection is happening, it is expensive. Like when the connection is happening, it's expensive. You have your TLS handshake, which usually terminates at the load balancer. Then you still have some states that you have to keep here. You have to communicate with the backend server to validate that particular user. So this is another HTTP overhead that you have to go through for 20,000 requests at that point. Now imagine that you have millions of users. If they are trying to connect to a small cluster of servers that cannot handle it, then we can now have another storm, which is exactly what happened at Discord in March. So they were trying to basically upgrade the configuration of their Kubernetes cluster. So they want each cluster to handle few number of pods. So instead of handling, let's say 4, they want it to be 2, then they will vertically scale instead. But the rate limiter that was supposed to manage the amount of connections that are coming in was not updated yet. So when they took down some servers, which they have some things in place, as we said initially, Discord is not a small team and they have good engineers. So what they will do is they will hand off gracefully some of the connection, actually all of the connection, to some other servers. And when they are done with that, then they will terminate that particular server. But before they could finish, the timer that they set ran out. And they still have 17% of total Discord users that were dropped off ungracefully. So what now happened is that 17% now tried to reconnect. And they've also not updated their rate limiter, which allowed lots of connections to come in. It overwhelmed the existing servers, and those servers died. And when they died, all the connections that were attributed to them also died ungracefully. So it now caused another storm, which is like a lot of people again trying to reconnect, and we can understand how that would go out of hand. There are still a lot of things that happened that led to their voice service going down, but in the context of this video, we just want to show that this is a failure mode that could happen. Let's talk about failure mode number 2, which is the easiest, or one of the easiest to understand. If you have several users on a particular WebSockets connection, so let's go back to this initial image. So just to make it easier, you have a single server and you have 4 connections. When one user sends a message, you have 4 fan-outs, or let's say you have 3 fan-outs. So that's a total of 4 messages. So when 2 of them are sending messages, you have 4 messages and another 4 messages. So that's 8. When 4 of them are sending messages, it will continue to scale like that to the extent that when you have 1,000 users, just 1,000 users on a particular server, and all of them are sending messages, let's say 1 message per second, then you would have a total amount of 1 million messages per second that you have to deliver. And 1 million messages per second is a lot of messages. And most of the time, a single server might not be able to handle that depending on the configuration of the server. This failure mode is called fan out amplification. Then the third failure mode is the proxy timeout trap. So usually when you have a load balancer like this, the load balancer tries not to keep some connections for too long. For instance, on Nginx and HA proxy, they have a default 60-second connection timeout. So if you have a connection through the load balancer and the connection is idle, that particular connection will be terminated. It would mean that if you don't update the configuration, every user, every connection that will be connected to that particular load balancer will be dropped every 60 seconds and they will have to do the reconnection afresh, which is something that you might not want. There are 2 ways to solve this. You can just update the configuration to have a longer time, which might work for you, or you can implement a heartbeat, which is basically, let's say every 2 seconds or every 5 seconds, you want the server to send a ping message to the user, basically check if he's alive. So you will send a ping message, the user will send a pong, then you can send a ping after another 5 seconds. Then if the user does not respond to 2 consecutive messages, then you can just assume that that connection is dead and disconnect it. Those are 2 ways that you can use to solve the proxy timeout issue. The next failure mode is the delivery gap and back pressure. When you think about WebSocket, you assume a particular contract. If I'm connected, I would receive every message. And when I reconnect on a disconnect, I should still get some messages. In a way, that should be a good assumption, but it doesn't work that way. So for instance, when these users were broken off this particular service, let's say this is WhatsApp or Slack, when these users were disconnected, any message that were sent by these other users would not reach them. And when they reconnect, they would also never get them. That's if you don't find a solution for this. So now when back pressure happens, sometimes you just want to disconnect some users. There might be some slow connections, and in most cases, you just want to drop them off and allow them to reconnect, and they'll be connected to the correct server where they are supposed to go. But within that period, there's a possibility that any messages that are sent by other users will not reach them. In these cases, there are different solutions that you might have, but we are still going to discuss possible solution for this failure point. But then the failure in this scenario is the fact that there is a possibility that even though you are reconnecting almost immediately, you might not still get all the messages. In some scenarios, that might actually be fine. Let's say a dashboard, or you are tracking the actual position of a particular thing, maybe in a gameplay, for instance. But if you need that particular message for audit trails and a lot of things like that, that you actually cannot miss any message, then this failure is a big failure point for you, and you definitely want to find a solution for it. Now, this will take us to the failure mode number 5, which is the autoscaling paradox. So as we discussed initially, if you want to scale this system, then we need to find a way to know when we are in trouble. That's these guys are doing too much work, which they are not supposed to be doing. Then would have a system, usually an autoscaler. It could be one in AWS or GCP or something like that, that would check some metrics from these servers and then add a new server, then connect them, and then we should be good to go. Okay, these 2 should be connected. This might seem fine, and usually is fine for typically a CTP workload, but for a WebSocket workload, it isn't. So let's say we have lots of users, let's say 120,000 users connections connected to these 2 servers. If they are idle, the CPU is not going to be doing a lot of work, because message fanouts are usually CPU bound, but the bookkeeping, like keeping states and all, they are usually memory bound. So the memory usage might be a little high, but the CPU usage is going to be low. So you can have 120,000 users on a particular server with 10% CPU, depending on the kind of server that you're running. So let's say both of them now have 10% CPU on both. The autoscaler, which, let me just put a box here. So the autoscaler here, the autoscaler can say, okay, we have some memory to spare. Since we only have 10% CPU usage here and 10% CPU usage, let's kill this server. If it kills this server, let me just bring it back just in case. If it kills this server, all the connection connected to this particular server will be severed. So you have about 60,000, in this scenario, about 60,000 connections trying to reconnect at the same time. And it will just give us the same scenario that we've discussed before, which is the reconnection storm. And when the reconnection comes storming in, there's a possibility that the CPU usage here would go up and this server might fail, or the autoscaler might come in time to save it to add another server. Then we'll go back to another steady state and it will kill the server. Then we'll have an autoscaling storm, a reconnection storm, and we'll just have to go back and forth. That's if the system doesn't fail completely. Okay, so that's scenario number 1. Then scenario number 2 is the fact that sometimes WebSocket systems don't fail the same way HTTP workload fail. Many times when an HTTP workload server is about to fail, you have your CPU skyrocket and your memory will just go up, and the autoscaler can pick up on that, then add more servers. In WebSocket system, there's a possibility that it can fail in such a way that messages are not being sent. So when messages are not being sent, then your CPU usage goes down and you might see a CPU usage of 6%, 10%, and the autoscaler can come in and say, we have more capacity, let's kill one server. It can kill the server and we'll go back to the reconnection storm and we can go back and forth, back and forth. So that's the 5th way your WebSockets can fail. So that we don't only talk about problems day in and day out, let's also talk about possible solutions. So let's go back to our initial diagram. If you know your system would not be handling thousands of users, you can just opt in for something like this. You have a single WebSocket server and you have several users, and it's going to be as simple as that. So that's solution 1. Then solution 2, you can have sticky routing. So for instance, in this scenario, we have a load balancer and we have 2 WebSocket servers. So we can come in such, usually when users are connecting, they are connecting to something like a room or a channel or something like that. So we can just say every channel A goes to server 1 and channel B goes to server 2. So when user 1 and user 2 goes to channel A, they are sent to server 1, and same thing for these 2, they are sent to server 2. So any message that they want to send would live on the same server, and then that data can be forwarded to them appropriately. This also has its own shortcoming, because when you have more users or more messages per second than a single server can handle, then you need more than one server to handle that particular workload. We can also have something like this. We just allow, which is basically the same thing as I described here, but you just have something like a routing service here, and routing service basically just tells you which WebSocket server to connect to. So now when you get to a workload where a single WebSocket server cannot typically handle what a single channel would want, let's say you want 10,000 users and you want all of them to be able to send messages at 1 message per second, which would be equivalent to like 100 million messages per second for the server. Okay, you know that that particular server might not be able to handle the load. So what you want to do is add more servers and find a way you can broker the messages between them. So this architecture is a simple one that you can use. You can always build on it. You introduce a message broker when messages are sent from user 1 and user 2 on the same channel to server 1. Then server 1 will send it to the message broker, which sends it to the server 2, because the server 2 is listening for that particular channel from the message broker, and then sends it back to user 3 and 4. So that's another solution. And for this message broker, you can choose to use Redis, you can use RediStream, or you can use their PubSub. RediStream is very similar to Kafka. You can use Kafka also, or any other message broker that you want. And then the last solution would be not to handle this at all. There are some cases where the headache is just not necessary. You don't have the engineering hours to face this, or maybe the budget to hire lots of engineers to be doing this, or you don't have enough users that would want you to go through this. So you can choose to use a managed service like Ably, Pusher, Firebase if you want, although I have my reservation about Firebase. Or you can use Celeris, which is a platform I've been building for the past 1 year, and the link to the platform is going to be in the description. We've not launched officially yet, but you can join the waitlist to get early access. This is my final word of advice. If you are building a SaaS that you don't need to manage or go through the headache of building your own real-time infrastructure, just go with a provider that is already doing this. And if you want to build something like this, then the question that you want to ask yourself is not if the WebSocket works, which we already know it works, is ask yourself, if 20% of your users at scale disconnect, can you handle the load when they are reconnecting back? Can your auto-scaling service handle it? Can your load balancers handle it? Will your services at each point be able to handle that particular load? Will all the servers that you have left be able to handle it gracefully? And that's basically all for this video. If you like engineering content like this, smash that subscribe button, and I'll see you later. Have a nice day.